Make sense? Yes?
Wouldn't a simpler way to do it be taking the first item of the list and then checking the rest of the list and removing any of those items if there's a duplicate found in that list, and then just iterating through the rest of the list each time? That means you don't have to compare the first part of the list that you've seen already again.
So think about that. So the suggestion is you start from the first and then you check in the rest whether this one exists. And if it does, what do you do?
And if it does, just drop that one in the middle away.
Okay, so you just return.
So you would compare the accumulator from the first item and compare it to the current part of the list you're at. And if you find the duplicate, you just return the rest of the list. And that would drop the duplicate item.
So you're still keeping track of an accumulator?
You would just keep, instead of a whole list of items, you just keep one item.
Right. So that would be the non-accumulator way of looking at this. And so another way of looking at this would be, if I had all the duplicates, if from the rest of the list I have removed all the duplicates, and then from that list, if I see whether this .doc is present, then I just return that list with the duplicates removed from the rest. If not, I return a list that has this doc and whose rest happens to be the duplicates removed from the rest of the list. So that would be the non-accumulator way of doing this. In other words, first getting all the duplicates removed from the rest of this list, and then using that to process the current element. The accumulator way would be looking at the things you have seen so far and see if you have already encountered this element or not. Okay? Questions? All right, so this was relatively straightforward when we compare to the bib sites. So for Monday, look at problem 2, variant 1. You're given a list and you have to verify whether the list satisfies 3 criteria. Okay? All right, so going back to our discussion yesterday, we were looking at how to overload a constructor, how to write a class that has multiple constructors. And so here for the circle, we wrote another constructor that this time just takes the radius and assumes that the center is going to be at the origin. So if you wish to create a circle that is centered at the origin, you call the second constructor and simply pass it one number. Okay? Now, you can have multiple, you can add more and more constructors to this. So let me write another one over here that takes in just the x and the y, but assumes a radius of 100. So once again, you could say super xy, and then this dot radius equals 100. So you can write multiple constructors. And again, for the overloading to be valid, you have to be able to tell the constructors apart from each other. In this case, you can tell them apart because they take a different number of arguments. So from your examples class, when you say new circle, after that, how many numbers you pass to that constructor determines which one of these 3 gets called. Okay? In fact, you can write a constructor that assumes that the center is 0, 0 and the radius is 100. In effect, you don't need to pass anything to the constructor. You assume that is 0, 0, and you assume that the radius is 100. And once again, those 4 constructors can coexist because you can clearly tell them apart. Okay? If you wanted to write a constructor that assumes that the y coordinate is always 100, but you specify x and radius, then if you think about writing such a constructor, the constructor would take in int x and int radius. And you would not be able to do such a thing because there already exists a constructor that takes in 2 integers. Okay? So the names of the parameters bear no meaning. Java is only looking at the sequence of the parameters to the constructors and what their type is. And so one constructor that has two integers, no matter what those integers actually represent, Java sees it as the same as another constructor in the same class that has, again, only two integers as parameters. So because you have two constructors that take two integers, if you say new circle and then pass two integers, we can't tell which one you mean to call. And therefore, Java can't tell them apart either. And so that is not allowed. So when you're overloading a constructor, you need to make sure that something about the parameters uniquely identifies that constructor. Either the number of the parameters is different, or the number is the same, but the sequence of types is different. Does that make sense? All right, so I'm going to write another constructor here. Circle actually I've written too many over here, so let me just start afresh. So we have a class circle that extends a shape, okay, and so it has an int radius right here, and so I'm replicating one of the constructors. So you'd call super xy, and this dot radius equals radius. Okay, so this is one of the constructors that I have already written. Now in your examples, let's say you create an example like this. (20, 10, -100). Okay. Now x equals 20 and y equals 10 is plausible, but I've passed a negative integer as the radius. So my first question is, will this example work? Will it be created successfully? And the answer to that is easy. Yes, it will be created successfully. However, should it work? It should not, because it makes no sense to create a circle of a negative radius. Okay? So far we have been relying on Java's type to weed out errors like this. I could not have called this constructor and passed it a string because Java can tell that. It expected an int, you passed it a string, clearly they are apart. But here the problem is more subtle. The type of the parameter I've passed, -100, is an integer. So everything that I've written in the constructor tells Java, yes, that is a valid value. However, I know from what a circle is that a negative radius does not make sense. So here I can no longer rely on Java's type system to weed out that error, because it is not a case of passing data of the wrong type. It is a case of passing an invalid value, but of the correct type. Okay? So the intended effect of this statement should be that it should stop Java in its tracks and say, I cannot create that object. Okay? Now, we can have somewhat feeble error checking by saying, okay, I'm going to somehow print an error message that says, you should not be doing this. But that's not quite strong enough. So Java provides us with a more elegant, stronger way of flagging that something that you told it to do, it could not do. In this case, I want it to stop in its tracks and say, nope, I cannot create the circle object that you have asked me to. Okay? And so this mechanism in Java is known as exception. exception handling. Okay? An exception is simply an object that your code can create when something exceptional has happened. Okay? Till now, we have been creating circle objects, and in our examples, we have been making sure that the parameters make sense. But that is largely because we have made sure that the parameters we pass make sense. Okay? Now we are going to build something into the constructor that flags out those invalid cases. And so how do we do that? Let's see. So I'm going to move this down to make space for it. Okay? And then right here, before I say this dot radius equals radius, I want to check whether the value passed to me is valid or not. Okay? So checking is rather easy. I just need to check if the value passed to me is positive. So here I can check if radius is less than or equal to 0, do something. Okay? But if that if statement, if that Boolean expression returns false, then continue saying this dot radius equals radius. Okay? Now, inside that if statement, I'm going to create an exception. An exception in Java is nothing but a specific object of a specific class. I'm going to create an object of that class, and I'm going to throw it. Okay? Whenever you throw an exception, it causes that method, or in this case, the constructor, to end right there. It will never make it to the statement this dot radius equals radius. And because it never made it to the end of the constructor, we say that the object was never successfully created. Okay? So down there in my examples, it will throw an exception. And on the very next line, if you were trying to do something with C, it will never get there because C could not be created successfully. Does that make sense? So as I said, exceptions are nothing but objects of certain classes. Now Java comes with a reasonably large number of classes, each of which represent a specific kind of thing that has gone wrong. So what we have to do is pick the correct one that signals the kind of thing that has gone wrong here. Okay? Now, if I try to characterize what has gone wrong, I could explain it this way. One of the parameters, one of the arguments to this constructor has a value that is invalid, that is illegal. That radius should not be negative. Okay? And so it turns out there's a kind of exception in Java that is tailor-made for this purpose. When you have called a method or a constructor, and one of the parameters that you pass to it happens to have an illegal value. Okay? And so I create an object of that class. The name of the class is illegal argument exception. Okay? So exception names in Java are fairly long because they are spelling out explicitly why they are being used. So what I do is I say new illegal argument exception. So that's the name of an existing class in Java. And when I create it, I get to pass to its constructor some sort of a message as a string. So that whoever called this constructor and made this mistake can then read that string in some way and know what went wrong. So here what I want to say is that the radius must be positive. This message can be anything you want. You want to make it as direct and descriptive as possible. Okay? So you create an object of illegal argument exception, and then you throw it. So throw is a new keyword in Java that we are learning. So you create an exception object, and then you throw it. Okay? And so if that if statement is true, it will go in there, create that illegal argument exception, throw it, and that will signal the end of this constructor. Questions? Yes?
Do like write return anywhere?
No. So I'm glad you asked. The question was, do we have to write a return anywhere? So when a method throws an exception, it is trying to chart an alternative path to its entry, to its exit. Normally, a method or a constructor would exit when it reaches the end of its block. If this were a method, then you would have a return statement. That would be the last thing it did before it ended. We call that a graceful exit. It ended the way it was expected. This is an exceptional circumstance. It has to sort of bail out midway because it cannot complete what you asked it to do. What you asked it to do was create a circle object. Here, it is bailing out and saying, I cannot complete what you're asking me to do. So technically, it's not returning anything because it never produced the intended result. So that's why we say we threw an exception. Okay? It's like if you ask a kid to give you candy. If the kid is in a good mood, they will return you the candy. If the kid is in a bad mood, they would throw a tantrum. The two are not the same thing. And so the tantrum would get your attention. And so that's the keyword throw. Will the rest of the code still run, or will all execution be stopped? So that's a good question. What happens next depends on what did you call that through this exception. So the thing that I called that through that exception was this line in my examples class. Okay? So normally what would happen right here is if you don't do anything, your examples class would stop right there because something just threw an exception, and you can't just slip that under the rug and pretend it never happened. You have to handle it somehow. Okay? We'll see how to handle it so that it can go further. But for now, the only reason we would create or try to create an example like this is to test whether our constructor actually behaved the way it was expected to. Okay? And so we know that this will not work. But we have to have some way of testing that when I call this constructor like this, passing it a -100, it behaves in the expected manner. And the expected manner here is that I will get an exception. Okay? So for now, we are going to call such exception throwing constructors only from a test. So that the only thing we do right now is ensure that the thing actually throws an exception. Yes?
Why don't you need an else statement for the rest of it?
So that's a good question. We normally have an if followed by an else. The else statement in Java is optional. Here, if the if statement is not true, I just want it to go to the next line, which it does already. Okay? And so if you wanted, you could have an else and then this dot radius equals radius be inside that else. But writing it like this, the behavior is identical. Okay? All right, so how do we test something like this? As I said, if you just type that line right there, because the exception is thrown, you are going to, your examples class is going to just run out. So when you run this program in Eclipse, you're going to get those red line messages again and saying it threw an exception and you didn't do anything about it. Okay? If you read the error message, Java may call it as an exception that was uncaught. Because the keywords in Java for exceptions, and many other languages actually, roughly follow a baseball analogy. So you throw an exception like a ball, and when something is thrown, somebody has to catch it. And so the part that we are not seeing here, what do we have to do here so that we continue? We take care of the error and we continue. That part is called catching an exception. Okay? And so when an exception is thrown but is never caught, Java will give you an error message along the lines of this exception was uncaught. Okay? We would not probably use the word uncaught in any other context except Java. You have to love programming and computer science in general. When we don't find a word in the English language that quite describes what we want it to do, we just invent one. Okay? So this is the uncatching of something. All right? Anyway, so we have how to test. So Boolean test for exception. So till now we were using check expect and check inexact. None of them quite capture what we want to test here. We want to test whether something, a constructor that we have written actually does throw an exception when we pass it certain parameters that we know are illegal. Okay? And so for that, we use a new method, test dot or t dot check constructor exception. Okay, it's quite a mouthful. Let me make sure I have the name correct. Hold on. Check constructor exception. Yes, okay. So in here, what are the different arguments it takes? The first thing it takes this time is what kind of exception do you expect? What is the exception object you expect with which error message? So here you would say, well, I expect an illegal argument exception with the message radius should be positive. Okay, let me make sure that's the message oh, must. Okay, so the expected message should be must. Okay, the second argument is the name of the class whose constructor I'm trying to call. Okay, so this is where this method gets a little bit weird. We don't actually say new followed by circle. We say, okay, I intend to call a constructor of that class. Okay, so that is name of class whose constructor we are testing. And then followed by that are all the arguments that we would pass to said constructor. So here's where we say 20, 10, -100. And that's the way we test whether a constructor that we have actually throws an exception. So this test will pass if calling the constructor of that circle class with those three arguments indeed produces exactly the exception with that exact message. If that does not happen, if this constructor either does not throw that exception or throws that exception but with a different string or doesn't throw an exception at all, then this test will fail. Okay? So therefore, this test is testing whether the constructor is going to throw the correct kind of exception or not. Right? Questions? So there were several questions that were coming up in earlier assignments about, hey, what do we do in the case where, things don't, the assignment says that some field should not have this value. So how do we make sure that that doesn't happen? And before this, we just advised you, okay, just create examples where it ensures that that constraint is obeyed. Now we need not be that careful. Now we can actually use exceptions so that our constructors can weed out these errors for us. And then we can write tests to make sure that the constructor is actually doing that. So this gives the constructor some enforcement capability. Not only is it there to simply assign values to our fields, but it is also there to check up when the values passed to it violate whatever constraints on the data we intend to have in there. Okay? The intention was for the radius to be positive. Can't enforce it if you just write it in a comment. So now our constructor can throw an exception. We can do the same thing for those width and the height of the rectangle. We can do the same thing for the side of the square. All right? In the book class, we could have done it with the price. We don't want a negative price. And so once again, we can use exceptions there. All right? Okay, so with that, we are going to talk today about a topic that in concept seems pretty simple. And we have been kind of riding on the fact that this just works for us. But now that we are in the business of actually writing classes, it helps to understand what we really mean. And the problem is very simple. It has to do with sameness. When I give you two things and I ask you, are the two things the same? You have to answer me, yes, they are the same, or no, they're not the same. And as I said, this is something that we've been kind of assuming just works. We know how to do it for simple numbers. And then the check expect is basically doing this. We give it two things, it's checking if they're the same, and the test passes if they are, the test doesn't pass if they're not. But what does it really mean when I give you two things and ask you, are they the same? It turns out the question becomes more interesting when we move towards more and more complicated data definitions. Okay? So let's start with some low-hanging fruit. If we just have numbers, integer numbers, then how do we test whether they are the same? We use the equals equals operator. So if it is integers. For example, you have A equals B. If you want to test it, then you would just say T dot check expect A comma B. Simple enough. If you wanted to test for sameness in the context of a test, you would use check expect. If you want it in your code somewhere, if one value is equal to the other, you use the equals equals operator. Okay? What about for doubles? Floating point numbers. So floating point numbers, if you try to use equals equals, Java will actually not yell at you. But we have seen the pitfalls of that. Floating point numbers suffer from precision problems. So when you are asking it, hey, is this double A equal to this double B, and you use equals equals, it is going to look for exact equality. So 2.000001, not the same thing as 2. Okay? So that is the reason we said not to use check expect when comparing double values. We have to check whether they are within a certain threshold from each other. Okay? And so if you are doing this in the context of a test, you would use check inexact, where it's A, B, and then a threshold. And what does this do? This basically says if the absolute difference between A and B is less than 0.01, then pass, else fail. That's the behavior of check inexact. Okay? How can you check if two doubles are the same in your code, not in test? Okay? So you shouldn't use equals equals. You should literally implement what I've written there if the absolute difference between the two numbers is less than some threshold. And so how do you actually do that? You can say math.abs, that's the absolute, of A minus B lesser than some threshold. So what you should not be doing is using equals equals. All right? Then we have also had a chance to look at sameness for some existing classes in Java. For example, how do you check if one string is the same as another string? So in the string class, there's a method called equals that magically returns us true or false, depending on whether they are the same string or not. Okay? How do we define sameness of strings? We know that a string is nothing but a sequence of characters. So two strings are the same if they have the same sequence of characters. Okay? But now our data is getting more complicated. So it helps to really understand what we mean when we say that two things are the same. So for numbers, this notion of equality is perhaps so burned in our brains that we don't stop to think what does it mean? What are the implications of saying two things are the same? But when the data becomes more complicated, it helps to think of what is really the mathematical definition of equality? What are the properties that we are looking for? Okay? And so you have likely seen these properties of sameness before. For our idea of what it means for two things to be the same, they should align with what we have understood from math is the notion of equality or the notion of sameness. Okay? So there are three properties. The first one is called reflexivity. If you have taken a course on discrete math, you've likely heard this before. Okay? So the first property that we want our sameness to have is that it should be reflexive. And that simply means that every object is equal to itself. Okay? So this seems patently obvious. Why would we even need to do this? But remember what we are trying to do here. Beyond the simple numbers, when we say two things here are the same, if we have written those classes, then we get to define what it means for two of these things to be the same. For example, we wrote the book class. What does it mean for two books to be the same? Well, we defined it as two books are the same if their titles are identical and if their authors are the same. That is our definition of what makes two books equal. Is everybody following? Once we have come up with a definition of what it means for two things to be the same, the hope is that we write a method that, when called, actually evaluates sameness for us. Okay? So now we are the creators of this class. We are going to write this method that is going to return a sameness. And therefore, it's very possible that we come up with a definition and write it up so that it actually isn't reflexive. So trivial as it may seem, it's important to keep these properties in mind, because since we are now going to define sameness, we have to ensure that our definition is sound and that it obeys these properties. We are the ones that are writing a method that is going to give us sameness. We have to make sure that that method obeys these properties. Okay? So the first one is reflexivity. The second one is called symmetry. So symmetry says that if, or rather, A equals B, if and only if B equals A. Okay? Why is this important? Let's say I give you two objects, A and B, and I ask you, hey, is A the same thing as B? Okay? Now, A and B are both objects of the same class. In that class, I have written a method called same that checks if this is the same as the other that I've passed you. It returns a Boolean. Okay? You wrote that method, and so when I call it A.same B, what symmetry is telling you that this method called A.same B should return the same thing as B.same A. If A equals B, that must mean B must be equal to A. If A.same B returns true, then B.same A returns true also. Think about if you make an error in implementing this such that that is not the case. Now, whether or not your method works correctly depends on the order in which you pass the objects. So that code would be extremely brittle. It's like you're tossing dice to see, hey, will it give me the correct answer or not? So it's very important that our definition of sameness be symmetric. The third one is called transitivity. In some sense, you can say that this is the kind of the logical extension of symmetry. It says that if A is the same as B and B is the same as C, then that must imply that A is the same thing as C. All right? So these are the properties of sameness. We can verify that for equals equals, this actually holds true. Okay? What about for our book class? We have a book that has a title, and for simplicity, I'm saying author. So two books are the same if they have the same title and the same author. How do I know if they have the same title? Well, it's a string. I have a way of knowing whether they are the same or not. Same for the author. So if I write a method, same book, book other, then I can say, well, this should return true if the title of this book is the same as the title for the other book, and the author of this book is the same as the author of the other book. I'm using the equals methods here because in the string class, there is a method equals that is doing what I want it to do. You can't blindly assume that you can call an equals method on any object that you have. But in the string class, there does exist a method that is doing the right thing. So I'm going to call it. Okay? Questions? All right. So far we've seen simple integers. We know how to do it. Floating point values, we know reasonably how to do it. Structured data, we simply come up with a definition of sameness, make sure it is consistent, it is reflective, symmetric, and transitive. And then when we implement it, we look at it likely goes, our definition of sameness depends likely on the definition of sameness for some of its fields. And so we find out how do we compare the fields for sameness, and then use that to implement the sameness for structured data. Okay. On Piazza, Ben Lerner said we shouldn't use dot equals for the assignment, and I was wondering why. I do remember that statement roughly. It matters what you are calling the equals method on, which is something I just said. The reason I'm calling equals here is because I want to find out the sameness of two strings. And for the string class specifically, I have documentation that says exactly what the equals method for that class does. Okay? As we will find out later, it is possible to call equals in Java on any two arbitrary objects. And that is what Professor Lerner was warning about. Just because Eclipse does not give you an error does not mean that you should be calling equals. What you need to understand is whatever equals method you're calling actually does for a fact what you want it to do. If you can ensure that, then you can call equals. Okay? For example, you can call equals on ILO string. That is not going to give you a compiling error. That does not mean that it's going to work. In fact, I can tell you that it's not going to work correctly. Okay? So you need to be conscious about, if I'm calling a method, I should know what it's doing. I should know the purpose of that method. All right? If we know that both are strings, then is that fine? Yes, then it is fine, because you can look up the documentation of the string class and it will tell you exactly what its equals method does. And if that is what you want it to do, then yes, you can call it. Okay? All right. So now let's come to union data. So we just looked at one. And so here we have I shape. Then we had an A shape. Then we had a circle, a rectangle, and a square. Okay, so we know what these classes and interfaces are. We know what they contain. So we can safely assume we know what these classes have. Now, I would like to define sameness between shapes. All right. Now, because it's a union data, first I have to be very clear about what I'm saying when I say two shapes are the same. Is a circle the same as a rectangle? No. Logically, that makes no sense. All right? So first, I know that shapes can only be the same as other instances of the same type. So a circle has to be the same as another circle. Okay? For my purposes of equality, I don't make that distinction even between rectangles and squares. There is a reason I have two separate classes. So I'm going to say rectangle can only be equal to another rectangle. Square can only be equal to another square. So that's my definition. Okay? How do I know if two circles are the same? Two circles are the same if they have the same location, the same reference point, and they have the same radius. Two rectangles are the same if they have the same reference point, and their width is the same, and their height is the same. Right? Similarly for the square case. So that is my definition of sameness for shapes. First, we have to ensure that this definition of sameness is consistent with reflexivity, symmetry, and transitivity. And then we have to actually implement it. Okay? So I'm thinking of a method that I can write here. Is it same or not? So that's a Boolean return type. I'll call it same shape. Is this shape the same as the other? That is the method I intend to write. Okay? For my examples, right here, I can create, let's say, a circle 2, 5, 10. I create another one 5, 10. Oh, sorry. Let me create another one that is the same. Then I have a rectangle. Zero, 0, 10, 10. And I have a square 0, 0, 10. Okay. And then my different tests are going to be check expect whether C1 is the same as C1 dot same shape. C2 returns me true. And C1 dot same shape of R returns me false. And R dot same shape S returns me false. Because one is a rectangle, the other is a square. My definition of sameness is that they should not be the same. And then just to check the other way around, I want to check that that is false as well. Okay, so those are my examples. They are not comprehensive. You need a few in there. I've just chosen to have these 4. All right. Now, with these examples in mind, let's try to implement it for the circle. I shape other. And here, let's review our definition of sameness. This circle is the same as the other shape if the other shape is a circle, and their reference points are the same, and their radii are the same. Okay? So the first part of my sameness is, well, the other shape has got to be a circle. Which means if the other shape is not a circle, I can just let go. I just return false, because there is no way a circle can be the same as any other shape. Okay? So the first thing I have to do is the thing that we have been avoiding all semester. I want to know if that other is a circle or not. Okay? But in this case, I really explicitly want to know that question. I'm not trying to find out the type to do something else. I literally want to know if it's a circle or not. That is the question. That is not the question that is leading me to something that I originally want to do. Okay? And so Java provides me with a way to check if that other's type is a circle. Okay? That operator is called the instance of operator. And so if other instance of all small, one word, circle. If this other instance of circle is going to return me a Boolean value, true or false. So if it is false, then I return false. All right. Now, if that if statement does not go in, it means the other is a circle. If the other is a circle, then I should be able to just convert it into one. And so I can force it to be a circle. Okay? This is called casting. Okay? Now, this is no silver bullet. You can't just cast anything into anything else. It has to be actually that thing. Okay? This is like trying to fit a peg into a hole. Can't fit a square peg into a round hole. Okay? We know this is going to work because this statement right here has ensured that the other is actually a circle. Okay? And so now we know that that typecast is going to work. And why do we need to do that? Because we need to extract its radius. And we need to extract its reference point. Okay? So temporarily, I'm going to break my own rule of not doing field of field, just to show you how I'm going to actually do this. So it's, return this dot ref point dot distance o dot ref point. I want to know if their centers are the same. And so I say if this distance is really, really close, and this dot radius is the same thing, and here's where I'm breaking the rule temporarily, o dot radius. Okay, it's technically not breaking the rule because o is really other, and so o dot radius is the field of a parameter that is allowed. Okay? And so if both of these are true, then it's the same shape as the circle. Okay? Yes, Caitlin. Yes, not exclamation means not. Yes. If it good question. So the question was, if I omit this line that is typecasting, and if I directly say other dot ref point and other dot radius, is it going to work? What do you think? This is where Java decides to be pedantic and bureaucratic about it. The if statement tells us that other is a circle, but Java still insists, no, 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 no. The type of other is I-shaped. I don't care if you have checks built in to ensure that it's a circle or not. I am not going to allow this. So you must make it happy by casting it to circle. And now you can say O dot radius. And it says, aha, O is of type circle. Circle has a field called radius. So you're fine. Okay? We do the same thing for the rectangle and same thing for the square. It's identical. For the rectangle class, we say if not other instance of rectangle, return false. Then we cast it into a rectangle. And then comes the part that's actually saying the reference point is the same. And in the case of rectangle, it would say the widths are the same and the heights are the same. All right? Let's see if this definition actually works. So everything seems okay. Let's make sure that it is okay. So the first one, C1 dot same shape C2. So which same shape is it going to go to? There are three same shapes: circle, rectangle, and square. Which same shape is it going to go to? Yes, circle. Why? Because C1 is a circle. Good. So it's going to go here, and the other is going to be C2, which is also of type circle. Okay? So it has gone here now. Other instance of circle. Is other an instance of circle? Yes, it is. So it's going to go past that if statement, going to be cast, and now it's going to check, hey, is the distance between the two centers really small? And it will turn out that yes, it is. The way we have created them, the distance is going to be 0. Or is the radius of one equal to the radius of other? Yes, it is. So it is going to return us true. Great. Works. C1 dot same shape R. Once again, dynamic dispatch is going to go to the circle. The other is going to be of type rectangle. Is other an instance of circle? No, it's not. So it's going to return false, as it should. Okay? Now, let's go to that one first, the fourth one. S dot same shape R. So now it is going to go to the same shape of the square class. Okay? If it's going to go to the same shape of the square class, the other is going to be of type rectangle. So then that if statement is going to say, is other instance of square? Other is of type rectangle. It is saying, is other a square? And the answer to that question is a rectangle a square? No, it's not. Is a square a rectangle? Yes, it is. But is a rectangle a square? No, it's not. So that if statement is going to return us false. Okay? Which is correct. We have just said that a square should not be the same shape as a rectangle. Now let's tackle that third case. Which same shape is it going to go to? Rectangle, square, or circle?
Rectangle.
Rectangle. Good. The other is S, which is of type square. Okay? Now, in the rectangle same shape, it is going to ask us, hey, is the other an instance of rectangle. So is S a kind of rectangle? S is a square. We just said a square is a rectangle because our class square extends rectangle. So the instance of, in this case, returns true. So it will go beyond, it will try to typecast that square object to a rectangle, which will work because a square is a rectangle. So the square class, because it extends rectangle, has a field called width, has also a field called height. And so it will check and and it turns out that both of them have the same reference point, both of them have the same width, and both of them have the same height. So R dot same shape S actually does what? It returns us true. What happened? I have two shapes. I call the same method. When I say R dot same shape S, it returns me a different answer than when S dot same shape R. Okay? One returns me true, one returns me false. Exactly one of them is correct. At this point, I don't care which one, because the other one is clearly wrong, and this should not happen. So our sameness just violated symmetry. And so it looks pretty innocuous, but as it turns out, there's a gigantic problem with implementing it this way. All right, so we are out of time. Let's see next time how to do this in a way that doesn't seem to have this problem. Look, for a successful cast, we have to make sure that the two objects share the same fields. In a matter of speaking, yes. For the typecasting to work, we have to make sure that their types are compatible with each other. And yes, practically that means the reason you cannot fit a square peg into a round hole is because, well, there are things about a square that make it fundamentally incapable with the circle. And so that's the reason. Okay? All right, I will see you on Monday.
We don't have class on Monday.
We don't have class on Monday. Do we? Yes. So